Hello, my name is Megan, and today I'm going to be demonstrating entropy using household items. Entropy is a thermodynamic property which can be described at a microscopic level or at a macroscopic level. Basically, the classical definition or macroscopical definition is that entropy is a measure of the unavailability of thermal energy in order to do work in a closed system. Entropy at a microscopical level is defined as a measure of the molecular energy states at a given temperature or pressure. Which sounds confusing, but it's actually quite simple. So for this experiment, I'm going to be using is a glass or a cup, pretty much anything you could put water in, and a couple. For this experiment today, we're going to be seeing how ice melting in a cup of water is going to be demonstrating entropy. It's going to be veering more towards the statistical or microscopical definition, because we're going to be talking about how the molecules in the glass of water and the molecules in the ice and the energy transfer and the heat transfer is all going to come together and basically describe how entropy is going to be demonstrated.
We're going to go over the governing equations that are associated with it. So to start, we're going to go over the general equation, which is the most standard equation of entropy, in which entropy is going to be set equal to the heat transfer over temperature. As you can see, S is a symbol for entropy, dQ is heat transfer, and T is a symbol for temperature. For the general equation, this equation is going to be for a reversible system in which the heat transfer is going to be in an exact differential, meaning it's going to be path dependent, while temperature is going to be based on an absolute scale. So for the next one, we're going to go over the change in entropy, which is the delta S is equal to S2 minus S1, in which delta S is the change in entropy, S2 is the final entropy, and S1 is the initial entropy. And the last equation we're going to go over is Boltzmann's equation. So Boltzmann defined entropy as a constant times the natural log of the energy states of a system. While Boltzmann's equation is used to define entropy in more of a microscopical or statistical way, it is also used to describe the disorder or randomness of a system. Hopefully now that you're able to see the equations that are associated with entropy, you're able to understand it on a more visual level. And now we're going to get into the experiment itself, so you have an even bigger visual of how entropy works.
So I have my glass of water, which is at about room temperature, and then my ice cubes. Like I said, this is going to be a very simple experiment, but it's going to be a good way of showing how entropy works. So the ice cubes are obviously in a solid state, which means that the molecules in ice are going to be more tightly packed. They can't really move around as much, whereas the molecules in a liquid state are going to be loosely packed. They're going to be able to move around more. So the ice is obviously going to melt because the water is at a warmer temperature than the ice. You might be asking, how does ice melting in a glass of water explain or demonstrate such a complex thermodynamic property? Basically, I'll show you how it works. So entropy in general, it's defined as the heat transfer from a typically warmer body to a lower temperature body. Obviously, from the ice melting, we could see that the heat transfer of the heat transfer is going to hit those ice cubes, and it's going to target those tightly packed molecules of the ice, and the heat from the water is going to transfer to that colder body of ice, and it's going to cause it to melt. Another way we can demonstrate entropy by showing this, because you may be asking, how does ice melting in a glass demonstrate such a complex thermodynamic property? And the answer is because entropy in a liquid state is going to be much greater than the entropy in a solid state, which explains why the ice is currently melting. It's kind of hard to see, but it is getting a lot smaller. That's because the energy and the heat from the room temperature water is targeting those molecules inside the ice, so they're finally melting. This proves the entropy statement, in which that the heat typically flows from a warmer or a hot body to a low temperature body. The ice cubes have completely melted inside of the glass. Again, hard to see, but they are completely melted. And when dealing with entropy, it's important to remember that when you're adding heat into a system, the entropy is going to increase. And when you're removing heat from a system, that entropy is obviously going to decrease. I know it's hard to see, but the ice is now completely melted. By the ice melting into the glass of water, that proves that heat will always flow from a hot temperature body to a low temperature body. So by this experiment, it basically proves the concepts of entropy, in which if you add heat into a system, the entropy is going to increase, and if you remove heat from a system, the entropy will decrease. So with that, it's going to be important to remember that entropy is still defined as the heat transfer over temperature. So the heat from the glass of water, like I said, it was at like room temperature. Even if it was a little colder, the ice would still melt because it's in a liquid form. But the molecules of the water attacked or targeted the molecules of the ice and basically transferred energy into those molecules. So the ice. Okay, so that concludes my demonstration on how entropy works using a glass of water and ice cubes. I hope it gave you a better understanding, because I know that entropy as a whole is very difficult to teach, and it's very difficult to learn because of its complexity. So I hope getting to see that the higher temperature from the water attacking those tightly packed molecules of the ice cubes shows that the entropy in the liquid state is definitely greater than the entropy in the solid state, which is why that energy was formed in the ice cubes and that energy was released, causing the ice cubes to melt.